Hello and welcome to another episode of Rustacean Station. I'm your host, Alan Wyma. Today I'm with Orson Peters, the creator of Glidesort. Welcome, Orson.
Thank you. Thank you for having me.
Yeah, I got so many questions, right? Now, why Glidesort? What got you interested to create this kind of sorting algorithm? Don't we already have enough sorting algorithms out there?
Do we already have enough? I mean, faster is better, I guess. And if you can go faster, that's good. There's definitely a lot of special purpose sorting algorithms that handles specifically strings or specifically integers. But for generic sorting algorithms, I would say most of them are rather similar, and Glidesort is not an exception. Like the core structure might be a bit different, but ultimately you apply the same techniques. Like it's still partitioning and it's still merging, and virtually every sorting algorithm invented in the last 50 years is one of those two. In this case, in Glidesort is both. But yeah, it's just a matter of speed and memory usage and improving in that factor. So is it enough? If you can show that it's better, I would say no. Then you can still make improvements.
Yeah, I mean, it's hard to remember like all the different algorithms and which one is better, best, right? Like,
Yeah.
what kinds of things? I don't know. Actually, there's so many questions I want to go with this one, right? I'm not too sure if I can go into what is Glidesort good for. Maybe we can talk a little bit about how did you get into sorting? I don't know. Would you call that like a hobby or getting into sorting algorithms, etc.?
So I think it's 8 years now or something. I implemented PDQ sort, which is now the default unstable sorting algorithm in Rust currently. And how did I get into it? I was in university. I honestly don't remember. I was just interested in it and I wanted to know how it worked. And I've always been the kind of guy that likes to reinvent the wheel. If someone, like some people call it not invented here syndrome, but I enjoy reinventing the wheel. I don't think I fully understand it until I've implemented it or I've done it myself. So I wanted to implement sorting algorithms myself. And I just looked at the standard library implementation. This was all in C++ back then. And I found it I don't know, there were inefficiencies there. And then I started reading some papers. And then I found a very interesting paper called Branch Mispredictions Don't Affect Quicksort, which went into that most of the time spent during sorting is in branch mispredictions, which essentially when you execute an if statement, it says, okay, the processors decide, are we going to execute this code or are we going to execute that code? And processors are really slow at switching from one piece of code to another piece of code, essentially. So they try to predict it. They just assume we're going to go this way and they're going to keep trucking on. And then if it turns out, oh, this choice was wrong, we're going to back up and undo all that work and restore the process. And that's slow. It's fast if the prediction is correct. And most branches are, in fact, very predictable, but it's slow if it's not correct. They found that during sorting, essentially, you're constantly branching. You find that assuming your input data is random, there's nothing to predict. It's going to be 50-50. In fact, if your comparison isn't 50-50, you're essentially doing a comparison that is not as informative. The higher the unpredictability of the comparison, the more information you're getting out of it. So it's fundamentally, you want it to be unpredictable. So it's not compatible with this branch predictor idiom that processors use. And they describe techniques that allow you to replace these if-else branches with essentially just logic. And how that works essentially is you have an index that is your output array, essentially, and you are copying the value to that index, and then you're conditionally incrementing the index. And this way you decide where the data goes rather than using if-else statements. So I looked into that paper. I was interested. I wanted to implement it for myself, and I did. And I found some minor optimizations. I also found major optimization back then to really efficiently handle low cardinality elements. I'll get back a bit more on that later. And that's how I got into it. I wanted to implement it for myself, and people liked it. People enjoyed it. The adoption for Glidesort has been absolutely, or at least the interest has been explosive, whereas pattern defeating Quicksort was more like a slow burn over 8 years. So that's kind of how I got into it, roughly.
I mean, for Glidesort, right? It must be building upon previous sorting, right? Because I think a lot of times you look at sorts and you're like, okay, wait a minute, you can take this piece, like you can basically Frankenstein it to a certain way.
Glidesort is, I wouldn't even say to some degree, Glidesort is very much Frankenstein's monster. It's bits and pieces from here and there. I took a lot of work from Igor van den Hove, who did similar to branch predictions don't affect quicksort. There was also an earlier paper, branch mispredictions don't affect mergesort. And then Igor really showed that you can apply these techniques to stable sorting as well, and like really showed this can be efficient in practice. And then I looked at that and I thought, again, I want to do this for myself. I want to implement this myself. I want to look at all the techniques that are available and make the best possible Frankenstein. And that's essentially what you get to with Glidesort. Then there are novel parts of it as well that weren't done before. Pattern defeating Quicksort's case, that was the low cardinality element. So to quickly explain that, when you are sorting, for example, cars, you might have thousands of cars in your data set, but there might only be 10 different brands. And if you're sorting on brand, that essentially means you have a lot of duplicate data. The actual data elements might not be duplicates, but what you're sorting it on makes them duplicates, essentially, for perspectives from the sorting algorithm. And when you are doing quicksort, which is essentially you choose an element and then you partition the data into stuff that's less than that element and stuff that's greater than that element. But you have to handle the case where, what if it's equal to the thing that you're partitioning by? Way back in the past, they really handled it badly. Like really ancient quicksort implementations, they were quadratic. If you gave it an input array that was all zeros, it would be quadratic time, because they put all the stuff that's equal to the pivot in one of the two boxes, and then they repeat this mistake over and over and over and over again. So you end up with quadratic behavior. But later, people said, you know, we're going to take these equal elements and we're going to put them in the box that they originally were. So if they were on the left, we keep them on the left. If they were on the right, we keep them on the right. And this way, the algorithm essentially becomes immune to low cardinality inputs. So you don't go quadratic anymore, but you're also not doing anything useful with this information. And what pattern defeating Quicksort did, what I did there was new, is I always put the elements that are equal to the pivot on the right partition, except if we've seen this pivot before. And you can do this, have we seen this pivot before? Using a clever check, you can do this using one comparison. And then if we notice, hey, we've seen this pivot before, so we know we put all the elements on the right, we're going to put them all on the left now. And that way, this is much better explained visually. But you'll just have to believe me that way you can very efficiently handle the case where there's many equal elements. You can very efficiently filter them out without doing any extra work. The only extra work you're doing is this one extra comparison. Approaches previously in the past, they use like three-way comparisons. Like in C, there's like this CMP function that returns -1, 0, or 1, and then the zero case is equal. And in fact, the Rust comparison operator is three-way, right? You have like ordering less, greater, and equal. What we actually do under the hood is we throw away that information for the most part. We turn in a two-way comparison because the processors are just much better at handling the binary case, and having to handle the ternary case essentially makes everything much slower to do it directly. So you would much rather do everything using two-way comparisons and apply this clever trick.
You'd feel that three-way would almost be better. Sorry for cutting you off. I'm just thinking, like, if you just sorted, like, the one that you sorted before, then you have something that's the same, then it would just make sense to put it next to it, right? So why would three-way be worse? I mean, I understand binary and why that would make sense, but just in my head, I just can't understand how. Okay, I know this one is here in my list, so that just seems like, okay, that goes there, and that's the end of the sorting, right?
So there's multiple things about this. So first, the three-way comparison is just slow because on the low level, on the processor architecture, if you're doing it based on branches, there are like instructions where you can like compute an address and then immediately jump to that address, and you could like have 3 target jumps, or you could do like a lookup table with a jump table, or you could do if else and then another if else, and that way you can have 3 targets. But all of those are relatively slow, and especially once you start doing branchless stuff where you are using this instruction called CMOV, conditional move, which is essentially an if, then copy this value to this value, but it's all done in one instruction without any branches. Um, all that stuff is binary. The fast stuff is binary. So that's on the low level. But even on the high level, there's the question, okay, great. You have a three-way comparison and you found out, let's say in the context of Quicksort, right? We're partitioning. You found out it's equal to the pivot. What now? Where are you going to put the data? You still have to put it somewhere. And in the binary partition case, it's very simple. There's an in-place technique where you find an element on the left that should go on the right, and you find an element that's on the right and should go on the left, and then you swap the two. And this way you can do it in place without extra memory. If you also have to handle equal elements, where do you place them? You still have to put a way for it. And then there's like algorithms in the past that put all the equal elements at the ends of the array. And then all the elements in the middle, it's like equal, less than, unsorted, greater than, and then equal again at the end. So it puts all the equal elements at the end. But that's 2 extra swaps per element, because first it puts it in the end and then it puts it in the middle. You could go over the entire array twice, count the amount that are elements that are less than the pivot, count the amount that are equal, count the amount that are greater, and then you can calculate the final position of each element and then go through the array again. That's another approach, but now you're doing 2 passes over it, right? Like, you have to know where the data goes. And if you are dealing with the 3-way comparison, now you suddenly need 3 output locations. You could do it that way. Like, it absolutely works. It's not a question of whether it works. It's just whether it's fast. And it just turns out, at least with our current processor architectures, that it's slower to do it directly.
Okay, that makes a little bit more sense, right? I feel like maybe we need to have a glossary before we continue to discuss about this, because you're saying pivot. I think I kind of understand what you're saying, because you're saying partition into 2 different partitions, left and right.
Yeah.
So do you mind to kind of give us simple, one-on-one, these are the terms that you should know as very basic sorting engineer?
To go one meta level higher, like Glidesort is as I said, it's a Frankenstein, right?
Mhm.
And it very much combines both mergesort and quicksort. And what I've been talking about so far is all based on quicksort. And in quicksort, the basic idea is you choose one element, and how you choose, that's one of the Frankenstein bits. But how you choose the pivot, and then you get that pivot, and then you partition the array. What means you check for each element, is it less than the pivot or is it greater than the pivot? And then you put all the elements that are less than the pivot in one place. I call that the left partition. You put all the elements that are greater than the pivot in some other place. I call that the greater partition. And then you recurse on these two. That is essentially the basis of quicksort, and it's very fast in practice. It is quadratic in the worst case if you choose a very bad pivot, so you need to intelligently select the pivot, and you also need a fallback algorithm. In practice, you will never hit this fallback algorithm if you're not facing an attacker. Essentially, in a modern algorithm, you have to face a specifically crafted input to make quicksort go quadratic. But when you do find that input, you do have to protect against. So essentially what you do is you check how many times have we recursed, and if this goes above a certain limit, you switch to another algorithm. That's another one of these Frankenstein bits. There's a lot of Frankenstein bits. But I said Glidesort was a hybrid of quicksort and mergesort. So mergesort is essentially a completely different approach than quicksort. Like, quicksort is partitioning. Mergesort is, as the name implies, merging. So you start off with small sorted arrays, and you keep merging them and merging them and merging them into larger and larger arrays. And at the most basic, mergesort essentially says recursing all the way down to the bottom level, and we say one element, that's a sorted array. And from there on, you can merge them into larger and larger arrays. More modern mergesorts, and that includes Glidesort, they have specialized routines. When you get to the really small sizes, they switch to algorithms that might not necessarily be optimal if you have very large inputs, but something like insertion sort or even bubble sort in some cases. Yeah, okay, it's quadratic, but if you have 16 elements, quadratic is meaningless, right? What ultimately matters is how fast is it in practice. You can just measure that. So what I've done in the past is just implement a whole bunch of different small sorting algorithms and just measured which one works the best. Yeah. What was your question again? I tend
No,
to
the
go on
question
a
was all about
tangent
having a
yeah,
glossary, so that way we can have a
yeah,
common vocabulary to understand. So pivot is where, so for your sorting, right, you only have 2 buckets or 2 partitions, as you call it, right? So a partition would be a group, right? When you start to
yeah.
initially go through your list of data that you're sorting. Pivot would be that factor that decides, is it less than or equal to? Because you do have the problem of equal to, right?
Yeah, exactly. So, I mean, that's the logic that PDQ sorts introduced, pattern feeding quicksort introduced. And I also use that logic in Glidesort.
Mhm.
So the default is that the elements equal to the pivot go in the right bucket.
Okay.
So,
That would be the
but
greater
you
than
still just,
bucket. So it's greater than or equal to.
correct, yes.
Okay.
But you classify this essentially using a single less than. If you have less than, right, and you take the output, if it's true, then it goes in the left bucket. And if it's false, that means it's not less than, so it's
Okay.
greater or equal, and then it goes in the right bucket. So using one comparison, you do this partitioning, this classification, if you
Now,
will.
may I ask, why not do the other way around? Why not do greater than, and then the other one is less than or equal to?
It's absolutely symmetrical. You could.
Okay.
The only core difference is that in pattern defeating quicksort is that if you detect to use the pivot earlier, that you then switch which side the equal elements go on. Because in the current behavior, it puts the ones by default on the right. And then it detects, hey, the ones that were equal, we already used this pivot, so they must all be in this partition. If we now put them on the left, we have a long string of equal elements, and we don't need to recurse on this at all.
Mm.
So yeah, it's completely symmetrical or completely arbitrary which one you do first, as long as you switch when you notice that you've used the pivot before.
But how do you know if you used a pivot before? That means you have to have another list of previously used pivots because you're just going to keep
You
pivoting
you
and keep bucketing, right? Or I call
you
bucketing and
would
keep partitioning, right?
you would think so, but no, you don't need to keep a list. So the simplest case is for an unstable sort like pattern defeating quicksort. You're recursing, right? You're a recursive algorithm, and because we know we are in the right recursion of a parent, and I've programmed pattern defeating quicksort so that it always puts the pivot right before the right recursive call. So to check if we used a pivot before, we only need to do one comparison to the element before array start, essentially. You do a out of bounds access one before your current recursive call, because you know that's where the pivot of our parent would.
You spoke like French to me. Sorry.
I'm sorry.
Yeah, sorry. I'm not a math guy. I like math. I'm okay with it, but I'm always very bad at it. To be honest.
To put it to more like in a glossary summary level, we can choose, at least in pattern defeating quicksort, we can choose where the pivot goes of our initial partition. And then our child calls, they get essentially passed the location, whether implicitly or explicitly, they get passed of where the parent pivot was. And then they can immediately look that up. You don't need to look at all the other pivots before that because they essentially form a chain. You're only interested in the maximum pivot that was used prior. Because you are recursively partitioning over and over and over again, right? We're putting the elements equal to the pivot in the greater than bucket, right? So that essentially means if as you recursively partition over and over and over, the pivot becomes larger and larger and larger. And the only way it can be equal, right? The only way our currently selected pivot in our current partition can be equal to the previous pivot is if it was the last pivot used, essentially. Because if it was a pivot earlier than that, we know it would be less than this greater pivot. A value equal to that pivot would not be in our current partition. It's just,
Okay,
we know that
I
because of
kind of
earlier
understand.
partitions.
Let me repeat back what I kind of understand. So you got your two partitions, right? And you're
Yeah.
saying that usually the next step would be go to the right partition, and then once you have your first left, that would mean not even, because again, if it's equal to the same, it'd still be in the right. So maybe we use some solid numbers because that might make it easier to me to
Yeah.
understand. So maybe if we have like, I don't know, maybe 5 elements is probably enough for me to start getting.
Let's say the first pivot is 6, and we're sorting numbers 0 to 10. And now we're in the right partition. We know that this partition only contains elements 6 through 10. We don't have to worry about elements that are 5 or less because those are in a different partition. So let's say we partition this thing again, right? And now we chose 8 as our pivot. 8 is not equal to 6, so we don't get into the logic about what about equal
Sorry, one
elements.
last question. When you're choosing pivots, so in my mind, I'm thinking that you would choose an element as a pivot, but you're not. You're just randomly choosing something to pivot on.
Random is one strategy. It's rather
Okay.
poor. What modern algorithms tend to do is that, I mean, okay, so random is kind of poor. If you were to choose either the lowest or the maximum element, you get quadratic behavior. The ideal pivot, like if we could magically select the ideal pivot, it would be the median. The median would perfectly split the element, the lists in two, and we get the optimal runtime behavior. That would be our ideal pivot. However, finding the median would essentially involve what would essentially be quicksort again. So there is this recursive algorithm, medians of medians, that essentially uses quicksort to select a pivot for quicksort. It's really fascinating, but that's also slow. So what we do in practice is we choose a sample. At the most basic level, you just choose 3 random elements and you choose the median of those 3. That's already a lot better than completely random. What Glidesort does is essentially a recursive version of that. So if array we're currently partitioning is large enough, it recursively selects 3 pivots, and then it selects the median of those 3 pivots. If it's not large enough, it will just select the median directly of 3 random elements. Or not random, but arbitrary, rather. You could randomize it to
Okay.
be resistant against attackers.
Yeah. I mean, you could theoretically choose 3 random numbers that are just so low or so like out of whack that it would just become quadratic now.
So in the case of the numbers, right, you're sampling directly from the domain, right? You could directly sample from 0 to 10. Glidesort and pattern defeated quicksort are generic algorithms. We can't directly sample from the distribution. We actually have to physically choose one of the elements in the array because we might be sorting something that doesn't even have like give me an arbitrary element.
Well, I'm saying like, okay, like say you had everything that was 4 digits long was majority, but then you had 3 random numbers in there, randomly in there, and you happen to be so lucky that you chose those 3 random numbers, they're only single digits, and you chose a median of that, you'd be way out of whack, no?
Absolutely. And the funny thing is, in practice, that doesn't happen
Yeah.
if you choose randomly,
I
right?
can think so,
But
yeah.
that's why I mentioned earlier, the only way you hit this like quadratic worst case if you face a malicious attacker.
That was another thing I wanted to go back to, sorry, was like, do people really do a malicious attacks like this? I mean, I guess so.
I've done it. I've shown in the past that the libc++ standard sorting algorithm is quadratic, specifically by using one of these attacks to construct an input. If you would sort that input, it would show quadratic behavior. Yeah, for all these algorithms, you can construct one of these quadratic worst cases. And there's 2 defenses against it. One is use randomization. And then as long as you keep your random secret, you are essentially reduced to the average case. You could still say, but we could get really unlucky. But you could also get unlucky and a lightning strike hits your server and your power goes out, right? That's
Yeah.
infinitely more likely than your random number generator selecting these pivots badly. Or you do what I did and you essentially say, okay, we did too many recursions. We're going to switch to a different algorithm now. And funnily enough, what fallback algorithm does Glidesort use? Glidesort's fallback algorithm is Glidesort. The only difference is it turns off the quicksort part and it only uses merging. And the merging has no quadratic worst case.
That's interesting.
Yeah.
Okay, you're definitely filling me with interest about I didn't know sorting was so interesting, to be honest. I feel like a weirdo for being interested in this topic.
I mean, I think you must have had a hunch, like you wanted to invite me and come talk about
Yeah,
sorting.
yeah,
So,
yeah. Like, I'm sorry if I made you feel bad about enjoying sorting, but no, it's definitely interesting because it's like I'm always interested how to solve like weird problems because I mean sometimes you can take pieces of these solutions and make new solutions to other interesting problems, and it's interesting to see how you can use these kind of simple hacks. It's like, well, I have like 1,000 elements and I got to sort them. How do I choose a pivot? Well, just choose 3 random ones, right? And
yeah.
that is actually a really interesting idea. It's like, well, yeah, I mean, you're not going to be exact, but at least it's better than trying to really get a median answer by summing all that up because you could have a million elements that'll take you longer than to sort it, maybe. I don't know.
Yeah, absolutely. It's like, I mean, there's a whole field of heuristics that like get applied in every field, and especially like heuristics are kind of a low-hanging fruit if you know that the problem you're solving is intractable. Like if you're trying to do the traveling salesman problem, we know that is NP hard, and we know you can't do that efficiently to get the optimal answer. So then it becomes very obvious. Okay, now we're going to use a heuristic, right? We're okay with getting a suboptimal answer as long as it's done in reasonable amount of time. But I think heuristics are especially interesting when you're not forced to use them, right? You could choose the median in sorting. You're not forced to do that, but it's faster if you do. And I think those are the most interesting heuristic optimizations when you're not forced into them, but they're still a good choice to actually do.
I mean, there's a lot of things happening in these kind of in your sorting, right? I'm thinking in my head that if you had like 3 elements to sort, I think glide sort may be overkill now.
For 3 elements, absolutely.
Yeah.
Glidesort does have a essentially, if your array is less than like 50 elements long, it has a fast path. It doesn't go into all the extensive logic, and it just uses the fastest direct code to sort your small arrays. In fact, I'm still gonna focusing more on that, improving that. For 3 elements, no. Most of the tricks here really come into play after like 10,000 elements. You really can start seeing the effects, and especially for a million elements, you can start seeing these orders of magnitude improvement.
I mean, there's a lot of swapping happening, right? And things being moved around. But does that mean that you need to kind of have like, I mean, is it something like 3x the amount of memory to hold it that you need to have kind of available? Trying to think about like what kind of resource intense is this going to be?
So Glidesort actually significantly improves upon that compared to the current algorithm. And so before I get to that, first, there's 2 kinds of sorting, stable and unstable, and you have both of them in the Rust library. The unstable sorting algorithm, the only thing that's really different on the guarantees it gives you, it doesn't guarantee that the order of equal elements is preserved. So in the case of numbers, it doesn't matter, right? If your numbers are equal, then you can swap the 2 and it doesn't matter what original order is. But let's say you are sorting a list of songs, right, in Spotify, and you're sorting them by duration. You don't want the order to suddenly start shifting all over the place if all the durations are 1 minute. You would expect the original order to be preserved for the equal element. That's essentially what a stable sort guarantees. If by the thing that you're sorting they're equal, they are kept in the same order as in the input. So the unstable sorting algorithm, PD pattern feeding quicksort is an unstable sorting algorithm, and sort unstable in the Rust standard library is an unstable sorting algorithm. These can be generally in place. That means that they don't use any extra memory at all. They strictly use in place swaps. So yeah, for that, the answer is how much extra memory does it uses? Zero, essentially. The stack. Glidesort is a stable sorting algorithm, and stable sorting algorithms have traditionally needed more memory. There are in place stable sorting algorithms. They're like Wikisort and Grillsort, fascinating things on you can look up on Wikipedia, all very slow. They go into like really academic tricks essentially to invent memory. One of the funniest things I've seen that one of these kind of algorithms uses is that you take a part of your array and you sort like pairs of elements in this array, subsection of your array. And now you know that these elements should be sorted, right? And now you can use each pair of elements as one bit of storage because you can swap the two elements and then you can detect, hey, is this pair out of order? That's a one. If it's in order, that's a zero. And this way they invent extra memory to use based on the fact that they're able to reorder elements. Tricks like this is what can make these algorithms really slow. I'm not saying that they all use this, but it's stuff like this. Um, so stable sorting algorithms to implement fast, they generally use some extra memory. The most traditional stable sorting algorithm is mergesort, just plain old mergesort. And as you say, it needs some place to store its elements. So when you merge two lists or two arrays of elements, what is generally done is that you move the smallest array somewhere else, like to temporary memory, and then you merge back using the gap that you just created in your array. And you can prove that as long as you choose the smallest of the two arrays, if you're sorting n elements, you need n divided by 2 memory. So that is the traditional memory usage. And if you go to the current Rust stable sort implementation, it's n divided by 2. That's how much memory you need. Glidesort improves upon that. All I can say is too much detail. Various techniques in this podcast. You can maybe ask me about specifics later. But one of the things it can do is it can take one of these merges and it can split it into smaller independent merges and then use an in-place buffer swap to rearrange the elements so that you now have to deal with two smaller recursive cases. And this way you can get this n divided by 2 down as much as you want. You can give Glidesort as much memory as you want. You can give it like 100 elements worth of stack memory or 1,000. You can give it as much memory as you want. It doesn't scale, it doesn't become any faster if you give it more than n elements worth of memory. That's the absolute maximum. But yeah, it can use as much as it wants. And I set up the default memory usage so that if you're staying under 1 megabyte of memory, so not in terms of elements, but actually in terms of bytes, right? If you give it, as long as the total size stays under 1 megabyte, it will use just straight n elements worth of memory. It will not try to do any memory saving whatsoever. As long as you stay under 1 gigabyte, it matches the current Rust standard library behavior where it's n divided by 2. And if it's more than a gigabyte, it will actively try to reduce its memory usage by switching to a strategy that uses n divided by 8. So 4 times less memory than the current Rust standard library sort.
Yeah. Now that you mention it, I did find very weird about this sorting, stable, sorting, unstable. Like, I think I used the unstable in a project and I forgot why, but I remember it told me I should use that one somewhere online. And I felt this is really weird.
I actually think the standard library currently explicitly says, like, if you don't need the stability, use unstable sort. It's faster and it uses less memory. That was actually a fun point that the standard library maintainers brought up when I talked to them, is if we do adopt Glidesort as the standard stable sorting algorithm, what are we going to do about this advice that we gave people to use unstable sort instead? Because on some platforms, for some input sizes, Glidesort is faster than even the unstable sort currently. That might change in the future again when the unstable sort in Rust gets improved further using more modern techniques. But yeah, up until now, the advice has always been unstable sort is much faster, but Glidesort has really closed that gap. It just uses more memory. And that's also one core difference if you are doing embedded programming. The unstable sort doesn't require any memory allocation, right? It's strictly in place. So at least with the Rust standard library interface, you can call unstable sort in core. But the stable sort requires a memory allocator, so it's not in core. You require at least alloc for it. But because it's implemented on slice, I'm not even sure if you get it in alloc. I would have to look that up. So yeah, using alternative interfaces like on the Glidesort crate, you can actually explicitly give Glidesort like, here, use this buffer. And in theory, that should be able to be used on embedded. Then again, I must say that using Glidesort on embedded is kind of fishy because it really, like, these order of magnitudes improvements, you don't see that until very large inputs, and you're not going to be sorting very large input on embedded systems, as far as I can tell, at least. So you're probably much better served on embedded systems to just go with whatever sorting algorithm has the smallest code footprint. So yeah, it's kind of a questionable benefit to be able to do stable sorting in fixed memory in that sense.
But do you know what's with the name stable and unstable? Because when I hear stable, that sounds good. Unstable sounds like my code may throw a bug just based on the name, right?
Yeah, I mean, absolutely. And it might. So if you rely on certain orders, that's the thing, right? Unstable sorting makes no guarantees about the order of equal elements. And one of the things is that's problematic is that this order might change if you change the algorithm, like from version to version, right? You might update your Rust compiler and they change the unstable sorting algorithm, and now its behavior for equal elements has changed. It's allowed to, right? It doesn't guarantee the order of equal elements, but if you somehow relied on that, then yes, that's a thing. Whereas the stable sorting algorithm, it's completely deterministic. The only thing that's technically not deterministic, if you're being really evil, is if you start writing a comparison operator that actually somehow executes logic in this comparison operator that's dependent on the order in which elements are compared. Yes, you can do some evil stuff with that. That part is not deterministic. But as far as the output order, it's 100% deterministic based on the input order. But that's not the case for unstable sorting algorithms.
Okay, so the word unstable means that you may get different results as the Rust code is updated for equal. That's what I'm trying to understand what the point of the name unstable and stable is.
Well, the name predates any sort of Rust context. The term stable sorting algorithm, I don't know who invented it or who coined it, but that far predates any Rust context. That's just a name they chose back then. It doesn't have any implications other than the order of equal elements is not guaranteed.
Okay, so the number of equal elements not guaranteed would be the meaning of unstable in this case.
Correct. Yes. And
Okay.
stable guarantees that order.
Okay. Now I can understand a little bit more. Oh yeah, yeah. This was unstable, may reorder equal elements in place, i.e. does not allocate.
Yeah.
Yeah. So it's like we went back to that idea of like sort by brand, right? And that would be
Yeah.
cars of the same brand, they may be in different order, but they're obviously sorted by the brand.
Yeah, like let's say, for example, you had a section of Audis, right? This talk is not sponsored by Audi, but you have a section of Audis, and they were in a particular order, and now you're going to sort all your cars, and now you might go back to the section of Audis. It's now suddenly internally in a different order, even though technically there was no reason to change that order at all. They were already sorted, right? They're all already in a block of sorted elements, so that would be unstable.
You're talking about running unstable sort twice on the same would be the same algo on the collection already sorted the first time. So you sort it
Well,
and then you sort it again.
it could be a subset. So actually, that's one of the things that Glidesort really does well, and that is sorting sequences of elements that already contain pre-sorted sequences. That's why Glidesort is like this Frankenstein monster of Glidesort and mergesort. Why do I want mergesort to be in the mix? It's specifically so I can take advantage of pre-sorted runs in the input. So I can take those runs as is and then use them in a merging routine rather than in a quicksort routine who would destroy the order. Why would we want to do that? Well, real world data, like if it's a time series, for example, it's like the sea level, it's probably going to be like going up, 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 and then going down, 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 right? So it already has this sorted subsequence in your larger data set. Even more realistic is that in a lot of cases, you will find like a programmer who needs to have some sort of collection in a sorted order and some new data comes in. So, like the first 80% of the array is already sorted, and then some new data comes in, and then you just call sort again on the new full size array. We want to be able to take advantage of the fact that 80% was already sorted, and only this new 20% needs to be merged into the already sorted section. Now, some might say, okay, but this programmer should have been using like a B tree all this time to keep this array sorted, or some other data structure that keeps its data sorted. While possibly true, often true, the reality is that people just want to get their code done and they want it now. And what's the easiest path forward? It's just to have a vector and call sort on it in a loop.
Okay. We did talk about that earlier today about if your collection is already partway sorted, and you can see that automatically. You do handle that case, right?
Yeah. That's one of the regressions currently I'm going to be working on. I don't have that logic because I had this fast path for small arrays. I currently don't check if it's already pre-sorted in the very small case. I should probably do that check there as well. But outside of that, yes, Glidesort, if it's already pre-sorted, it's essentially linear time. It will just run through the array once and it will, yeah, it's almost instant. But the beauty of it is that even if a part of your array is sorted, right? Even if in the middle you have a section of 1,000 elements that's already sorted and you're sorting like 2,000 elements, like half of it is already sorted, it will also speed up in that case. It will only sort the unsorted parts and then merge with the sorted part.
Now, here's a great question for you that you just immediately put into my head. How would you recognize that there's already a sorting there?
So what Glidesort does is it does one linear scan through the array and it just checks, hey, is this element less than the last one? Hey, is this element less than the last one, etc. And as long as that's true, it will keep accumulating this into a larger and larger section. And then at some point, it will become false or we've exhausted the array. At that point, we look at, okay, how many elements in a row have we just answered true for? If that length is long enough, right, it's a significant amount of the array. I think currently I implemented logic like it needs to be at least square root of the array size roughly. Then we, although I'm thinking about changing that logic. Anyway, if it's significantly large enough, we add that to our essentially our data structure that keeps track of sorted segments in our array. If it is not sorted, like we find, hey, it's out of order and it's not long enough, we skip a constant amount of elements, like we skip like 50 elements, and we turn that into what I call an unsorted run of elements. And it also gets added to this data structure. And what this data structure then does, it takes all these what I call logical runs, which can either be sorted or they can be unsorted, or they can be a specific case where it's two sorted arrays right next to each other. Then it starts merging these. And if it's two sorted arrays, it will merge them into one of these into this logical run that's two runs next to each other. If it is two double sorted, it will use a more efficient routine that merges four arrays at a time. It can take advantage of more efficient routines because I do this essentially this lazy step where we wait a bit with merging. If it merges two unsorted runs together, it will concatenate them into a larger unsorted run. It doesn't do anything. It just says, oh, unsorted, merge into larger unsorted. And by doing that over and over and over again, we can construct, if your array doesn't have any pre-sorted runs in it, using this process, you essentially construct a very large unsorted run. And then eventually, when it gets very large, when it would be about to not fit in the memory space we have allocated for Glidesort, then it will use Quicksort to sort this now very large unsorted run. So to answer your question, how does it detect these runs? It's essentially it scans through your entire array once.
That sounds very inefficient, right? It sounds inefficient, but I guess there's could be worse things.
Oh, absolutely. Like the overhead of one linear scan through the array. Also, as soon like let's say the array is unordered, right? It's completely random. The chance that a comparison succeeds is 50%. And if you do the math, that means on average, you'll find that you're going to do two comparisons before you find a pair that's out of order. So you do two comparisons, and then you detect, hey, this is not an unsorted run. Then you immediately skip 50 elements. So if your array is completely random, you're essentially doing a couple comparisons and then immediately skipping 50 elements. So it's only like 1/50th of the array that you inspect.
Okay, I see. Now we're back down to probability now, and that's something
Yeah.
I can flip a coin. I understand a little bit what's going on.
Yeah.
Okay, interesting. Yeah, I never thought about it like that because to me, like I did some CS questions or whatever for a job, and they were talking about how linear scanning is too slow. You shouldn't do that kind of stuff, or when you're streaming data, etc. But then what you're saying does make a lot of sense, right? If you're just doing simple yes no, right?
Yeah, that's the thing, right? Like sorting is inherently not a streaming operation.
Yeah.
Like you have that in databases. It's always what they call a pipeline blocker. The last element in your stream might be the smallest element that needs to be emitted first. And that is enough logic to convince anyone that you cannot do this in a streaming matter, right?
Yep.
So you have to have all the data collected in one place in memory before you can do any sort of sorting. You can do a partial, like you can do incremental progress, but ultimately the last element needs to be available before you can ever emit the first element. So when people say don't do a linear scan, it's slow, like in databases, that's if you're answering a question about a subset about your data, right? Like find me the smallest element or find me where Bobby lives. But sorting inherently involves all the data always. So doing full scan over all the elements doesn't meaningfully slow you down because, in fact, your n log n, you're going to probably doing the equivalent of log n scans over the entire array, and log n or log n plus one, it's roughly the same.
Okay.
And benchmarking it is like in practice, it's basically free.
I'm kind of curious though, besides this linear scan, is there anything else that's kind of that maybe people would think would be very inefficient, but actually works out quite well when you're doing sorting algorithms?
I mean, one of these things is quicksort in stable sorting. I mentioned like pattern defeating quicksort many times, right? I mentioned quicksort. And if you go to Wikipedia for quicksort, it will outright tell you that quicksort is unstable and that all efficient implementations of quicksort are unstable. Maybe by now it has been edited out since I am also mentioned in my talk, but at least last time we look at it right now, let me control F unstable. I think actually someone edited it out since my talk. I don't see it anymore. That's funny. I have a screenshot of it in my talk, but yeah, I think they edited it out. That's really funny. So I should change what I say. Wikipedia used to tell you that it was straight up unstable, and then all efficient versions of it are unstable. That is one thing that is just a misconception. Yes, if you implement quicksort in an efficient and stable manner, you're going to need extra memory. But mergesort also generally uses extra memory. And you can, using the logic that Glidesort uses, you can limit this memory to like n divided by 8 and still do quicksort on the majority of your operations. To do stable quicksort, you need, at least as far as I'm aware, there might be more efficient methods, but you need like an element, a buffer that is equal in size to your original array. That's what I use. But I also didn't want to give up the lower memory usage of Glidesort. Even in the case when you have a fully unordered array, it doesn't use quicksort for 100% of the operation. It will use quicksort as long as it fits in the scratch buffer. So for very large arrays, that is roughly n divided by 8. And then it will do quicksort on those portions and then merge those portions again using mergesort. So Frankenstein. Now I'm actually curious. I'm looking at the history of the Wikipedia article of quicksort. I don't know when that was changed. I'm not gonna do it right now. I'll look at that later. I find it very interesting.
Yeah. Okay. I do remember there's so many different types of sorts, and yeah, I remember that there's always like this, like say, like oh, if your data is X size, or if you're how do you say that, or if this, or if that, you should do it this way, you should do it that way. Maybe the question I have is when would Glidesort be a good use? It sounds like for large arrays or large collections, definitely it's a great choice, right? And whether it's ordered or unordered in all or some parts, it's also a great choice, right?
Yes. What Glidesort really is the first. So I'm not the first that like combines mergesort and quicksort. That combines this if some parts of your array are sorted. But what I would say that Glidesort really is the first to do in this category is to be what I call robustly adaptive. So that with the exception of a couple like maliciously chosen patterns, if a portion of your array is pre-sorted, it will take advantage of that. If a portion of your array has low cardinality input, it will take advantage of that. It is like it doesn't have to be all of it before it takes into effect. Most of this stuff does not use like these heuristics where you just happen to choose the right elements or inspect the right elements and then you happen to hit the fast path. No, it kind of is an emergent property of the algorithm. To me, that's very beautiful. I forgot your original question. I'm sorry.
Well, I'm just like saying, like, I kind of hear what it's good for, right? But
Yeah.
there, like, as you always hear, there's no silver bullet. Like, where would Glidesort be just not so good? I mean, we talked about, I guess, a 3 element array. Technically, it's not good for that. But you said that you can also detect that, and then you would just switch to another sorting algorithm. So, I mean, in that case, calling sort, it would just be, I mean, now would that mean that Glidesort is not good for it? Or would that mean that Glidesort accounts for this problem and switches to another
It's
implementation?
the latter. It doesn't account for it as well as I want to yet, and I'm gonna be working on that. The same thing, another thing that currency Glidesort emits quite a bit of code, like in your final binary. I'm also working on reducing that. It is a generic sort, and that I would say that means it's kind of generically useful. It is specific inputs, it will never be the best. Like if you're only sorting integers or floats, there are algorithms that use like SIMD or hardware acceleration kind of instructions that will blow Glidesort out of the water by another, like maybe not an order of magnitude, maybe even an order of magnitude, but several times faster, right? Specifically for integers or floats. If you are dealing with a lot of added data, like in a database context where you are sorting based on, like, I don't know, you're sorting based on brand again, right? But your car information involves 100 other data factors you need to drag around in memory. Glidesort might not be the best choice there either. If you're sorting specifically strings, there are more efficient algorithms than Glidesort. I don't know if they are implemented in Rust yet, but all these like data type specific or distribution specific optimizations that, yeah, you can bleed Glidesort. It's definitely not the silver bullet. But in terms of a generic algorithm, I think it is a very strong contender.
Now we keep talking about like less than or equal to and greater than, and
Mm-hmm.
these are just common integers and floats. That sounds very suitable, but then you're saying now it's not good for integers and floats. How does that?
Well, I'm not saying it's not good. So what Glidesort is a comparison-based algorithm, right? You can give it a comparison operator. That means
Okay,
you can sort anything with it. But an integer, it's not a black box, right? If I give you two integers, you can't just only say, okay, this one is bigger than that one. No, you can also look at, hey, this one has like the first 4 bits are 1111, right? You can look into the integer. One of the things that you can do with that is a thing called radix sort. Let's say you have random integers, right? 32-bit integers. And you can just look at the first 8 bytes of it. That gives you a number from 0 to 255. And you can directly place it in bucket 0 through 255, right? You can directly place the integer in the correct bucket based on its raw data value. You can't do that with just a comparison operator. All you can do is this one less than the other one? So these algorithms are less flexible, but they can speed up that way because they can directly look at the data rather than only through the very limited scope of a comparison operator.
I understand at the high level what you're saying, but I'm still trying to comprehend with the data representation part, right? So you're
Mm-hmm.
saying for integers and floats, you can look at a radix sort, which is going to look at
The raw
the
bits.
raw bits.
Yeah, it can directly look at the bits of the input.
Okay. Because to me, it's just like, wait a minute. Because at a high level, like I just keep thinking numbers are numbers, right? But I understand that the raw bits would actually make things.
Or let's say you write your library, to put it like less computer context. Let's say you're a librarian and you have a
Yeah.
book in your hand, and the book starts with, I don't know, it starts with a B, the title or the
Yeah.
author or whatever you're sorting it on in the library. You know that you can just directly walk to roughly wherever B is in that library, right?
Yeah.
You know the distribution of the library. Whereas a comparison based algorithm, in the ideal scenario, would start looking somewhere around, I don't know, what's the middle of the alphabet? I, J, H, somewhere
Yeah.
around there,
Mm-hmm.
right? It would start there. And the librarian will look at you funny. It's like, why are you moving to J? Well, it's the optimal place to do the next comparison to see whether B is less than J.
I see.
So you can have these distribution aware sorts. In fact, there's now also sorting algorithms that use machine learning to look at an item and then directly predict what location it should go to and then shuffle a couple of elements around. Because with the ideal algorithm, you should be able to predict directly the final location of the item based on the distribution it follows.
I want to go back to talking because before ones made a lot of sense about less than or etc. Now, would this make more sense if you have a compounded key of some sort, where you wanted to like you'd say like you'd have to somehow compute like a hash, then you would sort on that.
A hash is not order preserving. So yes, you can
Mm-hmm.
sort on a hash, and in fact, some algorithms do in fact sort on hashes for very specific purposes, but it's not order preserving. If you sort based on the hash, then the output order is going to be deterministic, right? You're going to get a particular result,
Yeah.
but it's not going to be in ascending order. To an outside observer, it's going to look completely random.
Maybe I could just be more direct, right? So
Mm-hmm.
you said, okay, numbers, strings, these things directly are not necessarily the best candidate for this glide sort. Now, what data type would be a really great candidate for this if I were to actually use this practically?
For Glidesort, you mean?
Yeah, exactly.
Anything? That's the beauty of it. As long as you can compare it, you can implement
Well, I can
the
compare
org
numbers,
trade for
and
it.
you said that integers and floats are not the best candidates. Maybe I misunderstood what you said then.
So Glidesort is fine and it will work. It's good. You can just go faster with integers or strings. It's not that Glidesort is better in integers or strings. In fact, it's better than like the Rust standard library sort
Mm-hmm.
for it. But by exploiting extra properties about the data, you can go faster than it.
I see.
That doesn't make Glidesort bad. It just means
Okay,
that there's a better option available.
I see. So you're saying, okay, I think I understand now. You're saying this is a really great, fantastic general sorting algorithm. But if you actually know your data type and you need to really get raw speed, there are better ones.
Precisely. That's exactly
Okay.
what I'm saying.
All right. Now I think I understand what you're saying now. So it's like, okay, this is like if you're doing strings or if you're doing numbers, this is not the best, theoretically, but it's great.
Yes, it is not the best. Like to claim it's the best, there need to be not be any
Yeah,
faster ones, and there are. So yes,
I understand now.
it's so good. It's so great. It's better than what you currently get when you call slice sort, right?
Hmm.
But yes, if you know specifically, I have 32-bit integers. There are faster algorithms to specifically sort that. They're just not
Got it.
generic.
Okay. Now I understand much more. Okay. Because it's like, wait a minute. These are comparison based. Like at a high level, it's like, okay, that doesn't really compute in my head. But you're saying if you know your data type, if you really need it fast, there are better ones. But if
Yes,
you don't really need that, whatever, you could just use this because they're
correct.
comparison based. As long as you can compare them, you can do it. So if you can
Yeah,
compare these things, you can do it. But if you want to go faster, there are better ways. Got it.
absolutely. Yeah.
Understand now. Got it. I think there is like lots of people out there who are like, oh, well, why should I use Glidesort? Because I know my data type. I can use this one. It's much faster. It's like, well, great. But that's not what Glidesort's about. Comparison based. This is probably one of the fastest.
Yes, absolutely. For me, that
Got
was
it.
very important. Also to look towards potential like standard library adoption.
Hmm.
But to me, the generic case is the most important one because if you have Glidesort, it works for everything. And then sure, you can go faster for us if you know specific data. I much prefer it if the generic case was just a lot faster
Yeah.
without having to go to specialty algorithms and stuff. And to just like, I don't know what percentage of time is spent sorting in the average program, in the average computer. I've seen wildly varying estimates by different people. But to me, it would be a nice contribution if that just becomes a bit less time and energy spent there.
Yeah.
And you do that by targeting the generic case and not highly specific algorithm that a couple people will use.
I don't know. I mean, I never really focused too much on the sorting algorithm behind like stuff. I just kind of like leave it to the library maintainers or the standard library team and say, okay, you guys handle it. I just want to call dot sort. And if it's slow, it's probably a language issue, to be honest. Most times I think it's a language problem rather than the implementation issue. Not to say that, I mean, sometimes obviously implementation is the issue. And that's why you're doing Glidesort over what you have currently in the standard library, right?
Yeah, I think it wildly varies. So something, for example, when you say like language issue, like Python,
Yeah, that's what I say.
for
It's funny.
example, right?
Everybody loves Python, but then they also pull it out for being slow at the same time.
Yeah.
You can never
So
win.
Python's like sort can be like, especially if you use a custom comparison operator, it's like very slow because you have to go to that comparison operator
Hmm.
many different times. And yeah, you're calling into this interpreted code every single time instead of just saying in the C world and the happy path. So what you see, like, is that a language issue? Partially. It also offers interesting optimization opportunities. Like the Python sorting algorithm is much more focused on reducing the total amount of comparisons than I would be in Rust. Right? If a
Mm.
comparison is comparing two integers, that's like I don't know, that's sub a cycle, right? On a modern processor, you can do multiple comparisons at the same time during one cycle. Whereas a comparison in Python could be hundreds, maybe thousands of cycles if you have to go through one of these generic comparison operators. So it's a completely different optimization landscape. Like, what is the most important thing to reduce? So even though it could be like you could phrase it as a language issue, I still think it's interesting that you then get different trade-offs in the sorting. What is the optimal choice for a sorting algorithm?
Well, yeah. I mean, if you're going from C to Python back and forth so many times, that is kind of somewhat of a language issue, necessarily, right? I mean, it's an implementation of the language.
Yeah, I mean, you can't go around that.
Yeah.
But what you could do, and you see that in the Python world, if you know you have floats, you can use NumPy
Yeah.
and you can call NumPy sort, and the NumPy sort can stay in C the entire time.
Yeah. But if you don't, or if you don't know any better, then you're kind of SOL,
Oh yeah,
right?
then it's gonna be slow. Yeah.
Yeah. So that maybe I just like to pick on Python too much because I'm not a huge Python fan. But it's interesting that you brought it up. It's like, so you're saying that for something like Python, obviously, it would be in the best interest to stay under the hood rather than calling back into Python, going back and forth. So it's like, okay, maybe Glidesort wouldn't work out for us because, like you said, it calls comparison a lot. We want to look for a sorting algorithm which does not compare a lot, right? Or did I misunderstood
So
what you said?
Glidesort is within a couple percentage points in terms of comparisons used compared to what Python would do.
Hmm.
because Python stays exclusively in mergesort, which has a slightly better. Actually, it might not even be true anymore since I adopted my new pivot selection scheme. I don't know. It's very, very, very close. It used to be that Quicksort was like use like 5 to 10% more comparisons than mergesort would be. So that's why Python never even used a quicksort. And also, Python was the original place where, maybe not the original place, but it's like the first place where one of these, they're called natural merge sorts. So the merge sorts that take advantage of pre existing runs in input. That's the first place where it really got popularized in TimSort in Python, precisely because doing this extra effort to minimize the amount of comparisons as much as possible was really worth it in Python because each
Yeah.
comparison was so expensive comparatively.
Yeah. That makes sense. It's interesting about that part. I mean, is there anything like Rust specific that you add in or no? Because you're just kind of always staying in Rust. So you don't really need to think about something like this.
Yes, actually, Rust has a different challenge, and I did talk about it in my FOSDEM talk as well. Rust has this thing called a panic.
Yeah.
They're kind of similar to C++ exceptions in that you can catch them, and they are what's known as unwinding exceptions or unwinding panics. They are problematic in Rust, at least as a someone who like dabbles in the unsafe, precisely because in C++ you can just say, hey, if you throw an exception while we're sorting this array, don't look at the array anymore, right? It could be in a bad state. It could be uninitialized or copied or whatever. Don't look at the array anymore. It's garbage. In Rust, you can't do that. You can't say like, oh, you panicked in your comparison operator. Well, you're not allowed to look at the array anymore, right? You can't do that in Rust. We have to be safe and sound always. And that's kind of a nightmare while implementing a sorting algorithm to also be efficient on the type or a comparison operator that could potentially panic, because you have to like essentially implement a lot of drop handlers and store all your state in structs. And then whenever a panic occurs, you look at your struct state and then you recover where all the data is in memory, because we're constantly like partitioning data to this buffer, partitioning that data to this buffer, and then restore all that data back into the original array. And it's really involved a lot of work. Maybe not unique to Rust, but definitely highlighted the most in Rust. The combination of the strong guarantees as a like a culture, right? You could say unsafe FN Glidesort and with just like don't panic in a comparison operator. But like if I wanted to be adopted in the standard library, we can't do that, right? We can't make slice sort unsafe.
But you are using some unsafe code underneath now.
Oh, absolutely.
There's no choice.
I think in fact doing like a merge sort without unsafe code is like literally impossible. You have to move data somewhere else and then move it back. You could do a quicksort. In place quicksort, you could technically do without unsafe code, but a merge sort is just literally impossible. And a stable quicksort as well. Whenever you're dealing with extra memory, that involves leaving gaps in the original array. And you could do it all in safe code if you added a bound on the sort which is default. And then instead of leaving some uninitialized garbage, you would leave a default value in the gap in the array, right? You absolutely could do that. But without that, it's essentially impossible to write almost any sorting algorithm without unsafe.
So right now, if people want to check out Glidesort, they have to check out the crate.
Yeah.
And that's just called Glidesort, I suppose.
Yes.
And but the plan for sure is to actually bring this into core, right?
Not core. It would be an alloc, but that is
Okay.
it would be the standard
I mean,
library.
within the standard library, that's what I mean by core.
Yeah.
Sorry.
It's just a nitpick because the core one can't allocate. That's like the embedded
Yeah.
subsection of the standard library.
Yeah. Okay.
There's also another competitor, Lucas Vultafer. I'm talking with him. Like maybe we can combine the best of his sorting algorithm and Glidesort in a package for the standard library, because I have quite a lot of code, both like in raw code and binary size, and he focused more on the smaller array cases and less code size. So I'm looking towards like working with him to reduce the code size of Glidesort and reduce and improve the performance on the very smallest array. Because I was mainly focused also for like, because it was mostly in an academic context where you look at like a million elements or 10 million elements, right? But for a standard library, it's much more important around like the 100 to 10,000 element mark, right? So I'm looking to improve in those areas.
You're not trying to talk with him to sabotage his work, right? You're really trying to work together on this
Oh,
one.
no, I'm trying to work together. And I also said like I would fully share credit.
Okay. Okay. I'm just making a small joke.
Oh, okay. No, no.
Yeah, I trust you. I don't think anybody's deliberately trying to do anything crazy. So, would you have to choose a new name? Like, would you combine each half name together, or would you call it Megasort or something?
I have no idea. I haven't thought about that. I'm actually talking to him later tonight. So, yeah, more news on that later. I have no idea.
Sounds good. I mean, if everybody's up for faster sorting, right? Nobody ever says, "Please give me slower. This is too fast."
Yeah.
So,
But the trade offs are because you can never, like, literally never, you can say this algorithm is faster than this algorithm. You have to look at like dozens of different distributions, like many duplicates, pre-sorted. Maybe it's like two times pre-sorted, concatenated. Are we looking at 100 elements, 10,000 elements, a million elements? There's all these factors, and they all like combinatorially explode in the amount of potential input distributions you could be looking at. So you can never say they didn't even count on like data types. Like even though you might be a generic sorting algorithm, the way you use comparisons or the way you access your data might favor integers over strings or very large types, right? Like you could have a type that's like 100 bytes for some reason. It is like a struct with 100 members, and you're going to sort that. How does it perform on that? There's all these kinds of aspects you have to look at. So it's you can never just say this algorithm is faster than another algorithm. There's always a trade-off.
now I'm kind of curious. Like, if you're going to replace what we currently have, I mean, that's the plan, right? Is there like going to be some kind of criteria that says, okay, for sure, speed is one, right? But is there
Mhm.
like a some criterion that you have to say, okay, these things would have to match for us to replace what we have, right? Because there must have been some kind of criteria to say, okay, this sort stable, sort unstable, these things. I don't know how you even say that. Like, it has to do X, Y, Z for it to that it works for the generic cases. I'm not sure if I'm making myself clear enough or not. Like, such as 10,000 elements, etc., that you were kind of hinting at before. Just want to make it a little bit more
Yeah,
clear.
so I did talk and present to the standard library maintainers, and I showed like for these benchmarks it's an improvement, for these benchmarks it's an order of magnitude improvement, and for these it's slightly slower. And we did go over that. It was except for one input, which was the what I mentioned earlier, like the small case where it's pre-sorted, where I currently just applied the generic path rather than the pre-sorted path. Besides that, it was always faster. That is compared to the current standard library implementation. It's not always faster compared to the competing implementation that is also looking to improve the standard library sort. So that's why I said maybe we can combine those two. There isn't like a hard, it needs to not regress on anything. I think, yeah, it's very subjective. So I think it's up to whoever is the standard library maintainer. Like they all have to approve of the change. So they all need to be happy. But there isn't
Yeah.
like a concrete, it needs to do this or that.
It would be kind of nice to have some criterion to say, like, okay, it has to be better than the current one at 10,000 or something. You know what I'm saying? Like, it's a little bit more kind of clear about what the benchmark is because you can never hit every single case as you're running into right now.
Yeah.
You can never be the best.
Yeah, that's definitely. I don't. All I can say is that's not up to me. I'm not a standard library maintainer.
Yeah.
That's up to them. Currently, there's only like a very minimalistic benchmark in the standard library. There's a by this other guy, Lucas Vultafer. He published like an extensive performance evaluation of his sort and Glidesort that also illustrates some of the back and forths. There are some distributions that I would still like to add to that to like highlight other aspects, but that's like a much better step. And using that research, we can present a much more complete package to the standard library maintainers to provide like for them to make a decision.
That's interesting. Were they a little bit shocked when they got this? Or like, oh, you're actually working on making this faster or better? Because we are
No,
using
actually
your.
not at all. And in fact, I've had contact with like some of them way before I went public. I even had like a public talk months and months and months ago on Glidesort. So it's not coming out of nowhere.
When you talk with them before, right? Like, hey, I'm working on a better sorting algorithm. They're like, really? This isn't good enough? Like, that's what I
No,
would be saying.
I've never gotten that reaction actually. No.
It's more like, of course. I mean, this is not good. We need more. We need better. I'm just kind of curious
Yeah,
what the reply was.
I think only in like the public reply I've had like people amazed that like sorting is like 50 years old or older and we're still getting improvements to that. I've seen reactions
Yeah,
in
as
that
my
vein
reaction
like is
was.
yeah, it's like isn't this a solved problem? And to that I can honestly say maybe at some point it was solved. I think if you apply the current algorithms to hardware from like 15 years ago or 20 years ago, I don't think Glidesort would be much of an improvement outside of these specific distributions I target, right? But Glidesort also boasts like a very big improvement in the random case when there's no pattern to exploit, right? That's just raw, low level detail, efficient implementation stuff. And that stuff is highly specific to modern hardware, right? I talked earlier about branch mispredictions and memory access patterns. I didn't even talk about what a large portion of Glidesort's complexity and innovation is in interleaving independent instructions. So I can take more advantage of modern processors' hardware parallelism, like instruction level parallelism. Modern processors can execute multiple instructions at the same time, structuring your code to be around that. That wasn't even like, if you talked about that 20 years ago, people will look at you funny, right? So they couldn't have possibly foreseen or optimized for that 20 years ago in a way that made sense. I fully expect in another 20 years for Glidesort to be completely stumped by something else that takes advantage of whatever is the hardware trends then. We might see, like, I don't know, maybe we'll all be using GPUs and we need to be much more aware of how GPU memory works, which has other quirks and stuff, right?
Yeah. I'm already thinking about like quantum computers, right? Where they don't have a binary path necessarily. They can have multiple paths, right? If I
So
understand
I
quantum.
actually did my master's thesis in quantum computing, so I am technically qualified to say some stuff about that.
Please, if you have something to say, I mean, I would love to hear how this would work in a quantum based kind of CPU.
I mean, to that I don't know. I only know the theory behind it and like the foundations of quantum computing, if you will. I cannot possibly say what a quantum computer, like a quantum CPU, would look like because that's so highly dependent on the specifics. Like we are at a point where if you would put it like in the equivalent of the transistor, right? We are having like, I don't know, 10 transistors. Like how do you execute a sorting algorithm on 10 transistors? Yeah, you can't even really talk about that, right? It doesn't make any sense. What we're missing in terms of quantum computing is like the lithography of quantum computing. That's what we're missing, right? How did we go from having computers be a giant fucking room to tiny phone in your pocket? It's lithography. We figured out how do we make these transistors really small. We need to figure out something similar for quantum computing. And until that comes, I don't think you can make any claims about what programming a quantum computer would look like. Right now, we are just simulating small circuits of a couple gates, essentially, a couple transistors. And you can already almost do useful stuff with that. Like, we're really getting close to being able to simulate certain, like, chemical processes, but that's using highly specific circuits. It looks nothing like general purpose programming. So, that is still very far in the future. Quantum sorting looks like, I have no idea.
Yeah, and I forgot totally about parallelism, right? I mean, because now most CPUs have multi-core, and that could easily be used for huge gains in sorting, right?
Oh, absolutely. That's definitely part of future work. I've been thinking about at some point maybe proposing Glidesort with, I was thinking of potentially doing it using async logic
Hmm.
to, because I already have logic for splitting up merges in Glidesort. And I already have like all the points identified where you could say, hey, now we're gonna do this in parallel. And you
Yeah.
absolutely could. I just haven't done it. Maybe I get lucky and someone else does it for me.
Oh, that part you're not quite ready to handle, or maybe after you get everything else done, that would be something next on the list to do.
Yeah, I don't know. You could call it laziness. I don't know. It's definitely on the planning. It's just not something I've done yet. It absolutely is. There's huge gains, but you would look also. I think I would have to like look more at like Rayon's model because it would
Hmm.
be targeted at Rayon. For me, I don't know why am I leaving also academia. I want to build stuff. I want to build stuff people use.
Hmm.
If I make a sorting algorithm, like, if Glidesort forever stays something where you have to explicitly add a crate Glidesort, then people are not going to use it, right? As
Yeah.
you say, if you want to sort something, you just call slice sort. And if it's like a two times gain, you're not going to change for that. You're not even going to be aware of it. So I want to use it. So if I want to do parallel sorting, I don't think anyone wants the standard library to suddenly start spinning up threads when you call slice sort. I don't think anyone
Hmm.
is waiting for that. But like I think Rayon has a sorting algorithms. I would definitely be looking towards that area to maybe see if I could integrate it there. I have to look at that.
Yeah, like that'd be something probably more of an opt-in. I think, kind of like with Derive, you have to, or sorry, Serde, the Serde Derive feature, you have to like actually add that feature in. So you don't want to be surprised. It's like, whoa, I got a little embedded
Yeah.
machine, and what I can't just spend like 50,000 threads. It's
Yeah.
way out of my interest.
People don't like being surprised.
I don't know. Depends on the surprise, I guess.
Yeah, I guess. You also get into the problem like I don't even know. I guess the standard, if you don't put it in core, but actually in the standard library, it does technically support threads. But you're always gonna get like this XKCD where someone is like, "You're breaking my workflow. When I press a space bar, my laptop heats up, and that triggers a user script. Can you undo
Yeah.
your patch that makes the CPU hot?" Right? As soon as you start spinning up threads in a stable sorting out the standard stable algorithm, there will be a guy like, "Hey, I'm running this kernel and I can't spin up threads," or "Hey,
Yeah.
I don't even know."
Understand. Yeah, yeah. That'd be nice to have opt into some stuff, right? I guess it depends on how much I really cared and how much I'd want that quickness and how much I don't mind to
Yeah.
spin up extra resource, right?
Maybe it would be another API call in the standard library, like sort parallel or whatever.
Mm,
But I don't know whether we would want that in the standard library. The Rust standard library is intentionally rather minimalistic,
yeah,
keeping stuff in third-party crates. So I think Rayon would be the place to do it.
awesome. We spent a little bit more time than originally planned. Maybe is there anything you want to say about Glidesort you didn't get a chance to say before we head off?
I don't really think so. I mean, for those interested, I guess watch my FOSDEM talk. I go into a bit more detail on like the specific algorithmics of Glidesort there.
Hmm.
No, I don't have anything prepared in terms of anything to shill.
No, try
No.
it out.
Yeah, I mean, obviously, go try it out. If you're running into something like, hey, that's funny, I thought this would be faster, please do let me know. Or a success story, like, hey, I tried it and it was much faster. I'm also interested to hear.
Yeah, we don't get enough of those success stories. Usually get a lot of complaints. People is just naturally like that.
Yeah, if someone puts it in and it works and it's great, and you don't ever hear anything from them because they're happy. But as soon as something breaks, then you immediately get an issue opened. So yeah,
I'm kind of curious
uh,
about what kind of replies you've been getting. I'm sure you've gotten some things that don't work, and it's like, okay, small pre-sorted array was a horrible experience compared to standard. Yeah.
I got one of those. Like the main things I've got response on was, where is there a parallel version? The
Okay.
code is too complicated to read. Please provide your benchmarks, which I haven't done yet. I'm still working on the paper and I'm planning to provide a separate repository where I have those benchmarks. I don't
Okay.
want to mix the, let's say, academic code with the publishable version because that tends to be academic code. I'm not going to spend hours and hours and hours on polishing that, you know? I don't want that in the same sphere of influence. But yeah, I've gotten one thing that says, hey, for this particular input, funnily enough, for an optimization I added after publishing it, where it was like, hey, this is suboptimal. And I'm probably going to fix that today or tomorrow.
Oh, that's cool.
It's an easy fix.
It sounds like there's not like what we call sort trolls, right? Like what you do, try to find an attack to dismantle this sorting algorithm.
No, it took me, like, when I found my attack on the standard library sorting algorithm in C++, it took 7 years for that to get fixed.
Mm-hmm.
And when I found it, I probably was already in there for I don't even know how many years. So that tends to move a lot slower. I guess you really need to look at all the details and how the Franken bits combine to find one of those cases. And hopefully there are none in Glidesort.
But you're looking for it. You want somebody to find it, right? Do you have offering bounties for these kinds of things?
Not in money. But please do let me know. I took great care, but you never know.
Yeah. When you got that bug report about that specific data set, were you a little bit shocked or were you just like, oh, that's interesting?
No, I'm actually not shocked because that optimization I kind of added after the release. In hindsight, it's really stupid. That optimization was essentially to skip a run if it's too short. Like if it's not at least square root n. Before I had that at like 50.
Mm-hmm.
And then I moved that to square root n. And then someone said, hey, but I forgot to then also increment the linear scan. So the linear scan, instead of being linear, it kept like jumping back by increments of 50. So
Okay.
technically not quadratic. It would be like n square root n, but also an easy fix. I implemented that optimization a bit hastily, I guess.
Oh, good. Well, Orson, thank you again for coming on and talking about Glidesort. This is quite interesting. I didn't know actually who you were until you told me today, and I looked up the sort, and there's your name right there. So I just thought you were some academic. I didn't know you already had code in the standard library for sorting. So it's cool to see that people are working on making their code even better for Rust, and that's pretty awesome.
Yeah, thank you for having me.